Hello everyone, welcome back. In this video, we will write a simple ARM7 program to display numbers from 0 to 255 on GPIO port 0, that is pin number 0 to 7. First, let's check if this code has any errors. No errors, so we'll go ahead with debugging. The very first thing we notice here is the assembler directive area, which defines a section of memory to store this information. Counter is the name I have given to that section of memory. Code indicates that that section of memory contains actual ARM instructions. Read only because we don't want any modification to be happening to this particular code during runtime. Entry indicates where exactly execution starts. Execution starts at the very first label that appears after entry. Start, count, delay, DD, all these are nothing but labels. End is an assembler directive which indicates the end of source file. Between entry and start, we can see the assembler directive EQU, which assigns certain value to human readable symbols. This particular value is the address associated with GPIO port 0 direction register, configures each port 0 pin as input or output. This particular address is associated with GPIO port 0 output set register, sets selected port 0 output pins high by writing 1 to the corresponding bits. This is associated with GPIO port 0 output clear register, clears selected port 0 output pins low by writing 1 to the corresponding bits. Before we start execution, let's open our GPIO port 0. This is your direction register, set register, clear register. The very first thing that we do is we load the address associated with GPIO port 0 direction register and place it in register R0. It's the same address as we can see here. Now we are updating R2 with the value FF and then storing it in that particular location. The reason we do this is to set the port 0 pin number 0 to 7 as output pins, and by default their values will be 0. Okay, let's see that happening. We are updating R1 as 0. R1 is our actual counter which counts from 0 to 255. At first, we are loading the address of GPIO port 0 clear register, updating R2 as FF and then storing it into the output. If any values were present here, it would be cleared by following this particular step. We are loading the address of the GPIO port 0 set register and storing whatever value is present in R1. Currently the value is 0, so output will continue at the same state and we will branch to delay. But from the next loop onwards, this is the main logic which will be sending different values to the output, that is from 0 to 255. So now we are branching to delay. I have kept a very low value, that is a value 1 in the delay, because I'll be executing it step by step initially. Once I explain the logic, I'll be changing this delay to a larger value so that while running continuously, you can see all the different values getting displayed clearly. Okay, so now the value loaded in R3 is 1. I'm subtracting it by 1 because of the set condition here. The CPSR will get updated and Z is set as 1, because of which this branch back to DD won't happen. Okay, and here we branch back to this particular line due to this branch and exchange. Okay, so this happens because when we branch to this particular subroutine through branch with link, already the link register will be updated with the very next address where we need to jump back once this routine is executed. Okay, so now we jump back here. R1 is incremented, then we compare R1 with 256. This performs subtraction. And if it's actually equal, Z would be 1. But as of now, Z is 0. So branch if not equal to is true. Okay. Hence we jump to count. What this will do? Now R1 is updated, right? So that will make the difference in this part of the code. The initial part remains same. Since there is no change in the output will still remain at 0 only. But now you will see the change. This LDR instruction loads the address of set and stores the value 1 at the output. Now you can see that output has a value 1. And we branch back to delay. Delay has only value 1 stored there. So it will get over fast and we branch back here. So R1 is incremented again. We compare if it already reached 256. That's not the case. So be clear. See, now you can notice the difference. This particular part of the code will now clear the value which is set in the port 0 pin number 0 to 7. You can see now output is 0. Okay. So now we go ahead, show the next value which is 2. In binary it is 1 0. And this particular task continues. Now I'll stop executing this code and I will increase the delay. I'll run this code continuously and you can see all the values getting displayed here. Or you can see the exact hexadecimal value if you check the last 2 digits here. This continues until a value FF is seen here. That is nothing but all these bits will be set as 1. Once all that task is done, the counter starts counting from 0 once again. So that's all about this code.